Now, suppose we want to count how many subsets we have of a certain size. So, for example, let's say we have this set. So first, let's go back, talk about two permutations of S, right, which is the most recent topic that we talked about. So the two permutations of S are, okay, so how many two permutations of S are there? And the answer is 12, and we use this notation, P of 4, comma 2. That means how many two permutations of this 4-element set are there? And the answer is 12. So now the new topic is, let's count how many 2-element subsets of S there are. In other words, subsets of S that have cardinality 2, okay, meaning, or you can say the other way, sets of cardinality 2 that are subsets of S. So here they are. Okay, so notice there are fewer in this example. And if you think about it, it makes sense. So like in permutations, we had 1, comma 2, and we also had 2, comma 1, because in permutation, the order matters, because a permutation is simply a list in which order matters. But when we talk about subsets, we don't have 1, comma 2 and 2, comma 1, because those are just equal to each other. So here are the 2-element subsets of S. Again, the subsets of S that have 2 elements in each. Okay, so now how many 2-element subsets of S are there? And well, we see there are 6, and we have this notation. And we read this as 4 choose 2. So this means I have 4 elements, and I want to choose 2 of them as my subset. So the number of possible ways to do that is 4 choose 2 or 6. So we have this notation, the number of k-element subsets of an n-element set is denoted n choose k. Here's a formula for n choose k. I'm not going to give the justification for it, but the book does, and you can look in the book if you want to know the justification for this. But here, I'll just give you the formula. If we have k between 0 and n, then n choose k is equal to n factorial divided by k factorial times n minus k factorial. And otherwise, n choose k is 0. All right, so suppose k is greater than n, then n choose k will be 0. For example, how many 3-element subsets does this set have? This set has 5 elements, and we want to know how many different 3-element subsets does the set have. So the answer is 5 choose 3. Now, what is that? 5 factorial divided by 3 factorial times 5 minus 3 factorial, which is 5 factorial times, divided by 3 factorial times 2 factorial. We can write it out. And now we can cancel some things, right? So the 3 times 2 times 1 can cancel with this 3 times 2 times 1, leaving us this, which is 20 divided by 2, which is 10. So if we start with the set of 5 elements and we want to know how many different 3-element subsets can we make, the answer is 10. Suppose we want, going back to cards, suppose we want to pick a 5-card hand from a standard deck. Okay, what is a 5-card hand? So first of all, 5-card meaning there are 5 cards. A hand of cards is simply a group of cards. And in a group of cards, order is insignificant. In earlier examples, in the previous section, we talked about a lineup of cards. There, the order mattered. But in a hand of cards, it just means a group of cards. It's like, think of it like just a bundle of cards. Order doesn't matter. So suppose we want to pick a 5-card hand from a standard deck. Okay, we want to pick a group of 5 cards from a standard deck. Question, how many such hands are possible? Meaning, how many such groups of cards can we make if all cards in the hand must be diamonds? Right, so I want to know how many different ways is it possible? How many different ways can I pick 5 cards? Can I pick a group of 5 cards? I don't care about the order. Can I just pick a group of 5 cards and such that all the cards will be diamonds? So there are 13 diamonds in the deck, and so what we have is 13 cards 13 diamonds, and we want to choose 5 of them, and the order doesn't matter. So we use n choose k. We use this formula when order doesn't matter, because this formula is used for subsets. Subsets are sets, order doesn't matter, right? As opposed to permutations where order matters. So here we're talking about groups of cards, hands of cards. The order of those cards doesn't matter. So I just want to take five cards out of 13. So the number of ways to do that is 13 factorial divided by 5 factorial times 8 factorial, which comes out to this. And now we can see we can cancel some things. So this 8 times 7 all the way through times 1 can be canceled with this 8 times 7 and so on, which gives us this, which simplifies to 1,287. Okay, next part of the question: how many such hands are possible if 2 of the cards must be clubs and 3 must be hearts? So making such a hand, right? Making a hand of 5 cards where 2 of them must be clubs and 3 must be hearts is a 2-step process. First, we want to pick 2 clubs. How many ways can this be done? How many different ways can we pick 2 clubs? In how many different ways? Well, this can be done in 13 choose 2 or 78 different ways. Next, we want to pick 3 hearts. And how many ways can this be done? Well, we have 13 hearts to start with, and we want to choose 3 of them. Order doesn't matter. So that's 13 choose 3 or 286 different ways. So now what is the answer? Well, the total number of 5 card hands containing 2 clubs and 3 hearts, to find that answer, we multiply the previous 2 numbers that we found. Why? Because for each possible choice that I make in step 1, I have, right? So for each of those 78 choices that I might make in step 1, I have 286 different ways to do in step 2. So that's really just the multiplication principle. It's not, it doesn't really look like the multiplication principle because we're not talking about a list. However, it's the same idea, right? We have a certain number of ways of doing one thing, and then for each of those different ways that we choose, we have now 286 different ways of doing the second thing. So the total number of ways of doing the entire thing is 78 times 286. Another example. So now we're going to talk about binary strings. A binary string is just a string of zeros and ones. Okay, so those are very important for computers. So how many 5-digit binary strings have an odd number of ones? Okay, so we're talking about binary strings, so strings of zeros and ones, using only 5 digits long, right? 5 digits long. And we want to know how many such binary strings have an odd number of ones. So let's examine a little bit what we mean. So for example, right, so here are 5-digit binary strings that have an odd number of ones, right? So this first one here has 3 ones. The second one here has also 3 ones. That's an odd number of ones. This one has 1 1, so that's an odd number of ones, right? It's 1 1, so that's an odd number. This one has 5 ones. That's also an odd number of ones, right? 5 is an odd number. Okay, so how many different 5-digit binary strings have an odd number of ones? That's what we want to know. So we can divide these strings into 3 non-overlapping categories. First category is strings that have exactly 1 1. Well, how many such strings are there? Well, to make such a string, a binary string that has exactly 1 1 there, right? So we're talking about a string of length 5, and one of the digits is going to be a 1, and everything else is going to be a 0. So there are 5 different ways to pick the position of the 1. One way you can think about it is we have 5 positions, and we need to choose one of those positions for the 1. Second category is strings that have exactly 3 ones. How many ways are there to make such a string? Well, there are 5 choose 3 equals 10 different ways to pick the positions of the 3 ones. Because when we pick those 3 ones, we don't care about the order of those ones, right? We just care about the position. So we have 5 different positions, and we want to choose 3 of them for the ones, to put the ones down. But the order of the ones doesn't matter. So that's why it's 5 choose 3. And let's just say strings, but not stings. Okay. Third category is strings that have exactly 5 ones. Well, how many ways are there to do that? There is only one way to pick the positions of the 5 ones. Okay, so now by the addition principle, the answer is just the sum of the sizes of the categories, right? We have 3 categories, non-overlapping. Each one has a certain size. We just need to add them up. So it's 5 plus 10 plus 1, or 16. Just keep in mind here, think about it. I should have said it a few seconds ago. How do we actually know that it's non-overlapping? How can you be sure that these categories don't overlap? Okay, and the key word here is the word exactly. Okay, so if we wouldn't have had this word exactly here and here and here, then we would have had to worry about overlap among the categories, right? Because a string that has 3 ones, it's also true that it has 1 1. Okay, but now that I added the word exactly, that makes sure that these are non-overlapping categories, right? If a string has exactly 3 ones, then it cannot have exactly 1 1.